Okay, so thank you for watching this short abstract presentation for the DFRWS 2021. So I'm Raymond, and today I would like to present the topic about the chasing walking path using smart lighting system. So first of all, for the introduction, as just give you a brief introduction of what actually the smart lighting system is. Smart lighting system actually is a subsystem under the building management system, which is called a BMS. So because BMS actually is used to monitor and control the device, electrical device within the building. So in our university, because we have an advanced cybersecurity lab, so we also want to explore the possibilities of using IoT systems into our campus. So that's why we install a smart lighting system in our advanced cybersecurity lab, not only to figure out are there any security or vulnerability issue, but also we would like to explore the forensic capability for the smart lighting system as well. So as you can see in this image, so this is our advanced cybersecurity lab. So all the light within the cybersecurity lab actually is controlled, or actually is we install the smart lighting system in the advanced cybersecurity lab, so that when we go into the lab, the light will automatically turn on and turn off. So that actually is also saving the power bill as well. So this figure is our smart lighting system layout. So you can see, in fact, this smart lighting system consists of a web applications, as you can see it here, the web the server, and there's a ZigBee gateway that wirelessly connected to the LED light. So the LED light actually that actually embedded with a ZigBee controller, and there's a sensor to detect whenever there's a human walk through to it. So the web applications actually is not only used to monitor the situations of the LED light, but also actually you can change the behavior of the LED light as well for better management for our lab environment. So the LED light actually is wirelessly connected using the ZigBee protocol. So that's why there's a ZigBee gateway right there to send and to receive and send the signal to the LED light directly. So this is another figure to show the smart lighting system layout. So you can see in here we have 15 sensors, 15 lights, and there are in total 7 sensors. So when there is someone that passed by the sensor, then you can see the light actually will automatically turn on. So using this figure as an example, so if there's someone walk through the sensor 1, then you can see the light 2 and 3 will automatically turn on. So if he walk inside to the lab, then the sensor, for example, like the sensor 7 will then automatically detect someone pass by, then the light 6 and 12 will also automatically turn on, so and so forth. So because as you know that in the previous diagram, I show you that there is a web applications that can retrieve this the sensor signal. So in fact, we can also utilize that to see if we can make it as a forensic use, because it is where the information is very useful if I can know someone go into the lab and his walking pattern as well. So actually we develop a Python program to retrieve the informations from the web applications by ourselves, and then we query those sensors periodically to see whenever the light is now turning on or off. And we can also, so then we just put it in a CSV format to actually record the pattern and the behavior of the sensor as well as the LED light on-off behavior. So actually the results are quite impressive, because when we're trying to analyze those data, we can actually predict, or actually we can track when someone walk into the lab, and also when someone is which location he is currently located at. So for example, if you're using this prediction as an example, so if you can see the first indicator in the bottom left corner is that the LED light 2 actually is being turned on at 12:49.15 seconds. And then from time to time, you can see that LED 6 and LED 11 actually turn on later on continuously, and then LED 7 is also being turned on as well. So using this kind of information, initially you will only know that, oh, okay, that light is turned on after. So if the LED light 7 turn on after 11, then actually it's just the pattern of the LED light. But however, we can actually use these informations to actually check if someone is walking to the PC, and then accordingly, so you can also see, so if the LED light actually is being turned on and then turned off, that means that someone is actually walking far away from the sensor. So we also do this experiment, and then we just go in to have a walk around to the lab, and then we found out that the LED light information are actually very useful and very accurate to detect when someone walk or pass by within our advanced cybersecurity lab. So To conclude, actually, we discovered that actually we can use the sensor data of the smart lighting system for forensic investigations, because in the old days we only rely on the CCTV, which in most of the cases, if sometimes the CCTV is malfunctioning, then we might not be able to check if someone is really walking near to some locations or not. So using the smart lighting system's sensor data can become a cost reference check. If there is also a CCTV that's right there, then we can actually adjust and synchronize the time to actually have a stronger proof of someone is walking near a machine or near another devices. Also, so because we can actually, if we do not have a CCTV, actually these informations can also be considered as a very useful digital evidence for checking someone is walking within a indoor locations or even outdoor locations if possible. So in the future, basically we would like to actually set up a smart living lab on the system, and we will actually test more subsystems and find out their forensic capabilities, because we are actually trying to build up a so-called smart campus. So we feel that actually there will be a lot of useful sensor data that can provide us more forensics capabilities, and also it can also be considered as some kind of digital evidence. And that's all for my presentation.
Hello and welcome to this presentation on enhancing traditional forensic investigations using IoT traces from smart buildings. We will look at how IoT devices and the traces generated can be useful to provide additional insight in classical forensic investigations. We'll also discuss which main challenges are presented by the analysis of these devices and propose a method to approach them. IoT devices can broadly be divided in industrial IoT devices and smart home IoT devices. We'll focus on smart home IoT devices, which are an ever-growing market composed by multiple segments: security systems, smart things, and smart assistants, which often interact with each other directly or through cloud services. IoT devices can be direct targets due to reduced security implementations and access to sensitive data. At the same time, they can be digital witnesses, as extended data is collected by these devices about their surroundings and the interaction with the users, in order to provide the needed functionality. We'll focus on this aspect. So, why collecting this data? Data collected by these devices can be useful in traditional investigations in multiple ways. It can help reconstruct the sequence of events, either by logging presence of people directly or indirectly by recording environmental conditions. A sudden change in temperature might indicate the beginning of a house fire. A sudden drop in temperature detected by a radiator valve may allow investigators to pinpoint a break in time, as we can see in the image above. Some devices may also record images and sounds useful for identification of persons, as recently happened in Germany, where audio from an Alexa device was used in the trial. They can also contain hints about authentication information or other devices that may expand the investigation perimeter. So, where is the data we're interested in? We can find it in multiple locations, each with different challenges. Locally, we can find directly the data on the sensors or the gateway devices, such as a camera or a smart assistant. We can find it on hubs or aggregators used to centralize the device management, such as Home Assistant or OpenHAB, or on smartphones with companion apps installed. Remotely, we can find it on the servers of a device vendor. Data stored locally on the device and sensors is often limited in retention time due to limited storage space and is often not persistent. Additionally, it is raw data, which needs additional interpretation to appreciate its meaning. Remotely stored data has often better retention and is better structured. However, it generally incurs in jurisdiction issues, as well as issues due to privacy laws like GDPR. These same laws, however, can sometimes be useful to obtain data when consent of the owner is present. They can also be useful to establish a corpora of information during the study of new device in a controlled environment. Smart hubs can particularly be interesting to analyze. We can see in this example that it's pretty easy to detect the presence of a person at home and even in a particular room, as highlighted by the changes in the light switch or the linked iOS devices. Finally, multiple changes are linked to IoT analysis. Detection of pertinent device or traces is among the first steps of a forensic process. IoT devices pose a particular challenge in this aspect, as many times they are hidden or may be mistaken for traditional objects, such as the case here with a Shelly light switch or a Taido radiator valve. Additionally, acquisition of IoT devices is often challenging and requires a very technical approach. Access to data on cloud services is generally met with constraints due to jurisdiction and can thus be a long process. Finally, even when the data is obtained, the meaning is not always clear, and understanding these traces may require extensive experimentations. In light of the value of these traces and the challenges in obtaining and exploiting them, we propose a multi-step approach to the IoT investigation on crime scenes. Upon discovery of a new device of interest on a scene, a study in a control environment is proposed to assess which traces are obtainable from the device itself, the companion apps, and eventually cloud sources, and establish the investigative value of these traces. This data is then fed in a knowledge base shared by forensic practitioners and researchers alike. In the final step, the data is used to train investigators on most common IoT devices, sensibilize them on their possible usefulness, and upon investigation of the crime scene, this data will help the investigator prioritize which object to collect based on the forensic value of the traces they can expect to recover from a device. That will be all. Thank you for your attention, and get in touch if you have any questions.
Hello everybody, my name is Hannes Spiegel. I'm a PhD student at the University of Lausanne, and I'm here to talk to you about how connected devices change the use of object traces. Now, as you are all aware, there is a gap between the physical and the virtual world. You are also likely aware that there are devices such as IoT, for example, that are allowing us to gap these bridges and using digital evidence to pronounce to give an opinion about what is happening in the physical world. Now, those IoT devices are becoming more and more prevalent and are opening up new avenues for investigation. Today, I'd like to talk to you about one of those avenues. Let's suppose we have a car accident with a driver on the run, and on the scene of the incident, we find a tire trace. Now, with classical tire mark analysis, we will be able to match this tire trace to a suspected car, or more precisely to the tire that is mounted on this car. We may then infer that the same tire was mounted at the time of the incident, and we may even argue about the person that was driving it. This is, however, mostly based on circumstantial evidence. This changes as soon as we're looking at a connected car. Last year, a tire manufacturer announced that they will now be producing smart tires that tell the car about the state of the road and the state of the tire itself. At the moment, we do not know whether this data will be available to analysts or investigators and what format this data will take. But it is safe to assume that there will be data to be recovered that allows us to infer about what tire was mounted at the time of the accident. Equally, smart cars store a lot of data about driving, about settings like the driver's seat, the settings of the rear mirrors. All those informations allow us to give an opinion or about who the person was that was driving the car at a given moment, or at least they may allow us to do so. I am of the opinion that currently we are not able to do that. There is a need for more awareness Most investigators do not know this data may exist, and crime scene investigators are unlikely to recover it. There is a need of interdisciplinary work. We need to work together with specialists from behavioral sciences and classical forensic science to see whether we can find sufficiently robust data to make those inferences. As always, when you're working together with people from other disciplines, there is a need for adapted language, so specialists can understand each other and can use precise language to describe what they're doing. And finally, there is a need for an evaluative framework. All those links that I presented you before are they have some uncertainty linked to them. So we need a framework that allows us to combine those uncertainties and give an overall opinion. Thank you very much for your attention. I'd like to invite you to read my short paper and to contact me with your ideas as well.